Okay, good morning, everyone. Welcome to my talk. My name is Yang. I'm from U Waterloo, a new faculty member there. So today, I'm going to share with you a story of finding needle from haystack. Okay, this is a joint work with Winston, now at U Michigan, Yifan Zhang, my student at U Waterloo, and Dr. Bill Noble at U Washington. So from yesterday, David and James talk, we all realize that machine learning is shifting the modern biomedical research paradigm. So on one hand, right, given the biomedical data, we want to train a powerful machine learning model to predict some disease of interest, right, either cancer, non-cancer, with high accuracy. However, we are not only interested in learning a model of high predict power. More importantly, we want to learn the biomedical insight from it. So to be more specific, we want to interrogate this machine learning model to generate testable hypotheses, which can be disease-specific. Okay. This hypothesis could be in the form of, say, disease-specific biomarkers, disease-specific interactions, disease-specific causals, and disease-specific pathways. Okay. So in this talk, I will focus on disease-specific interactions. Concretely, we are more interested in these non-additive interactions, defined as those interactions which cannot be further decomposed into smaller units. Using this toy function as an example, right? The interaction x1, x2, they are non-additive. And this function, this interaction x3, x4, they are still non-additive. But for this interaction x5, x6, right, they are additive because they can be decomposed in the log space. Just want to make sure we are on the same page. So finding these interactions from machine learning model is super challenging because we need to address these three questions. First of all, machine learning model generally be regarded as black box. So how to interpret these models to understand interactions? And then among these quadratic number of feature interactions, right, how to score them so that these non-additive important interactions can be ranked the highest. And lastly, even among these highest ranking interactions, there are many false positives. How to distinguish these false positives from these true positives? Okay, these are the three challenges we need to address. So that ideally, what we want is we want to discover a subset of non-additive interactions from a machine learning model so that they are very likely to be relevant. And meanwhile, we don't want to have too many false positives. Here's our setting. Given this input data, a sample by feature matrix, we want to train a generic machine learning model to predict, say, some disease of interest. After that, we want to interpret this machine learning model to induce a ranking list of feature interactions so that the higher ranked feature interactions will be more relevant to the phenotype we are interested in. And meanwhile, we want to provide a confidence estimation for each of these interactions in the ranking list in terms of a metric called FDR, or false discovery rate. And this FDR is defined as the expected ratio between the number of false positive interactions among all totally discovered interactions. In the setting of this ranking interaction list, so if we cut off somewhere, and all the interactions above this cutoff threshold will be our total discovered interactions. But we don't know, right, among these, how many of them are false positive. That's why we need to estimate from data. Conventional methods such as Benjamin-Hirschberg, they need to estimate FDR by dealing with p-values. However, in the setting of very complex machine learning model, there's no straightforward way to estimate p-value, making this problem extremely hard. Okay. So here's our workflow. Okay, the first step is when we train this machine learning model, we want to use this interpretation method, such as the gradient or Shapley value, to learn and to get a pairwise feature importance anyhow, even though we know that these are not really characterize this non-additive effect. Why? Because all these attribution methods, they try to attribute or marginalize the contribution to the final prediction to this pairwise feature. So it does not necessarily mean this non-additivity. Therefore, what we do is we want to distill this non-additive interaction effect from this observed reported pairwise importance from, say, Shapley interactions. What we do is, for example, this IJ pair of features, and we want to get this non-additive interaction effect by distilling it from this reported pairwise importance, subtracting this prediction-dependent marginal effect, and further subtracting this prediction-independent feature bias. And all these GI, GJ, and B, they are these learnable functions. So finally, we try to use a technique called knockoffs to control the FDR. The key idea is, for each of these features, we try to generate a knockoff feature, serving as a control to estimate FDR. So this knockoff feature, they are manually constructed. As the name suggested, they are false, but to some extent, they resemble the original feature. So what do I mean by the resemblance? Okay, so from high level, the knockoffs are constructed to preserve both the inter and intra correlation structure of the original input, so that they can be equally correlated with noise and signals. After we have these knockoffs, we just concatenate with the original input, and then we feed into a machine learning model to induce a ranking list of the interactions. Now, these interactions for these features, it contains both original feature and the knockoff feature we provide as the negative control. So we record their feature type, the labels. And then the FDR estimation, the high-level idea is it's based on the knockoff involving interactions. Okay, so the idea is the truly important original interaction, they have a very large score. But for these irrelevant interactions, as well as the knockoff involving interactions, they should be comparable in distribution. So we just try to estimate FDR by top-down, looking at this ranking list. And we calculate the FDR in terms of the ratio between, so here the denominator is the original count, and the numerator is the difference between knockoff original pairs and the knockoff pairs. So we try to evaluate our method on many simulation functions. I just show one, which is a relatively easy one. Okay. So we found that the commonly used baseline, right, the permutation-based p-value, together with this Benjamin-Hirschberg, surprisingly, it cannot control the FDR. For our method, we first tested on a multi-layer perceptron architecture. We can find that our method can successfully control the FDR. Further, we tested on a bunch of machine learning models, such as XGBoost, LightGBM, vectorization machine. All of these, we can control the FDR. So lastly, we apply our method to a real data set about the Drosophila enhancer data set. So it contains transcription factors and histomorphic features. And then the goal is to predict the enhancer status per sequence. So the task here is not about prediction. It's about how to find these important interactions contributing to the enhancer activity, okay, subject to FDR control. So, and then for this particular data set, it contains a curated list of these ground truths, the TF-TF interactions. And meanwhile, we can, for this, out of this list, because it's partial list, we can use the literature support. The result shows that for all these, labeled in star, they are these ground truths. Right? So we found that, okay, indeed, their reported FDR is truly low. So to sum up, we aim to build a general pipeline for data-driven scientific discovery. Remember, there's always three problems to solve. One is how to deal with this black box machine learning model. The answer is we need to use interpretable AI to assign an important score anyhow. And then how to prioritize these truly important non-additive interactions. We need to use the synergy distillation. And lastly, among many false positive interactions, how to choose the truly important ones. We should use knockoff-based FDR control. So this is a pioneer work to first demonstrate to the society that the interpretation of machine learning model can achieve statistical guarantee. Thanks. I'm ready to take any question.
I wonder what's the runtime overhead of your methods. You showed an example, I think, with 36 features. Does it scale to hundreds or thousands of features?
So the runtime is very easy. It's very quick because when we estimate this function to calibrate to distill this interaction effect, we use a generalized additive model, which is super fast. So it will not cost notably extra. There's no notably extra cost.
More questions?
Thanks for your talk. Have you thought about going beyond pairwise interactions and looking at higher order interactions?
Yes, so we did some initial exploration. So this is a quite challenging problem. We can manage to control the FDR. However, because the haystack grows exponentially, so it will definitely sacrifice the power. So we are trying to find maybe some clever way, right, to make it still achieve the power. So this is some ongoing work.
I think especially if you're looking at your application of looking at, for example, transcriptional regulation, not all combinations of all transcription factors will occur. It will always be a finite subset of them, and you could look at finding side information already as a prior to kind of constrain this exponential space, maybe.
Yeah, that sounds a good idea.
Thank you. Okay, let's do one more question.
Hi, interesting talk. I was wondering, you mentioned about the manual curation of the knockoffs. Like, can you talk more about that?
Oh, so the knockoff is not our work. This is a seminal work from Candice group at Stanford. So the basic idea is given a sample by feature matrix, and can we create a matrix with the same size so that these two matrices they just exactly preserve this first order, second order moment of these feature statistics, so that it can be used as a control, a reasonable control.
So these are simulated data, or?
We try, no, so this knockoff is just like a generative model. To given one data, you generate another data as control, which looks realistically. And of course, for simulation data, you generate a simulation-based knockoff. Right? For real data, you generate a real data-specific knockoffs.
Thank you.